homework that's closing on Wednesday.
Okay.
So do you have any questions on that? If we're able to look at that?
No, I haven't even looked at it yet.
Okay. Okay. If you need, since you've been sick, if you need more time before you take the exam, just let me know. And I can extend also the due dates on the homework and stuff like that. Okay.
Okay.
Okay. Sounds good. Now the schedule is to have an exam review on Wednesday, and then have an exam on Friday. But like I said, if you need more time, we can still do the review on Wednesday, but then I can wait to send down the exam until you're ready for it. The week after that is break week for us. So,
Okay.
okay, so that sounds good. Okay. Oh, switch to student. Go. Okay. We're done with time response. And we're just going to do block diagram reduction, and this is the last thing before the midterm. There's also homework for it. And so basically we're going to be learning about Mason's gain formula today. And you're just going to do this by hand and upload your answer there. And then this one is just multiple choice. Multiple choice. And multiple choice. So, okay. So that it would be good to do that before the exam. It's not due, but it'd be good because those are the kinds of questions that would be on the exam.
Okay.
Okay, let's do block diagram reduction. This is a fairly straightforward topic because it's similar to when you have a resistive network and you're going to combine series and parallel branches and then come up with an overall resistance. So, so very similar to that. Okay, but we don't add the same way. Here, again, if we had three resistors in series, they would just add up. But when we have a block diagram and we have three blocks in series or cascaded, you multiply them together. And so the output CS is going to be the product of these three transfer functions times the input. And we can look internal to the system. We can call this variable x1, and it's going to be R times G1 and G2. Okay. And we could call this x2, and it would be, again, G1 times R. Okay. So basically what we're looking at is just those three transfer functions multiplied together. And these transfer functions could be anything. 4 over s plus 10, 1 over s, just a constant 7, different things that each one of these things could be. Okay?
Okay.
Okay, we just multiply together. Okay. When we have parallel subsystems, again, for resistors in parallel, we've got the 1 over 1 over R1 plus 1 over R2 plus 1 over R3 kind of deal. We don't have to do that here. When things are in parallel, we have to end up with a summing junction. This is a pickoff point here. So these are all RS, and then we're just taking that RS and feeding it into 3 different systems. But coming back together again, we've got to say, okay, how are we putting this back together again? And this is a summing junction. So we're just adding, and then whatever sign we have on the summer, we're adding or subtracting each one of these. Okay? So multiplication, and then we have addition for parallel subsystems. And then I'm going to go over how this feedback system works, but in general, again, we have 2 things in series here, so we can lump those together. And we have 2 things in series, so we can lump those together. We'll find out that through something called Mason's gain formula, that we can take everything on the forward path and lump it together, and then we can have the feedback path that we call it, and the formula for that is 1 over 1 plus the loop gain or minus the loop gain. So if this is a minus here, this is a plus down here, and if this is a plus, then this is a minus. So there's a change of signs there. When we're looking at blocks and moving them around, here, if we've got our transfer function after the summing block and we want to put it before the summing block, again, to do like we did in circuit analysis and combine resistors together, what we have to do is put it on both paths coming into the summing junction. So this CS right here would be RS plus or minus XS times G, and this is RS times G, XS times G, and that's what CS is equal to. So they're functionally the same. Same thing with this, if we want to move from before the summing junction to after the summing junction, it's okay to put the GS, but now this feedback path has to be 1 over GS. Here, when we have a pickoff point and I want to put it before the pickoff point, the one that had the transfer function is going to be just have a gain of 1, but the other 2 legs are going to have a gain of 1 over GS. And so when we have GS times 1 over GS, that's just 1. GS times 1 over GS, that's just 1. If we have it before the pickoff point, we just put a GS in every one of the paths. Okay, so this is, and I've got a couple of homework assignments where you're going to combine blocks together and stuff like that. But it's just like playing a Rubik's Cube. You just keep on looking for combinations that will simplify. So here are some examples. We've got these 3 things going back into the summer. So we can combine these 3 things together, noticing that we have a minus for H3, a plus for H2, and a minus for H1. So we leave the minus here. And since that's the same sign as right there, that's going to be plus H1, minus H2, plus H3, and then a minus sign here. So that's how the signs come off. Is that making sense? We have 3 things feeding into this summer. We can combine them together because they're in parallel. And then we have these two blocks. What was that?
I get the signs for the
the plus, summary is in the plus, but why is the one minus?
Well, this one is plus here.
Yep.
So we're taking whatever CS is times H2 and we're adding it to the other things for whatever reason. So all this is based on the system that you came up with for your control system.
Okay.
So again, these are just arbitrary, like in circuit analysis, we just had arbitrary circuits, and then we had to come up with what the resistance, overall total resistance is for the circuit. Well, here we have to come up with the overall gain or transfer function of the circuit. Okay, so we're not looking at why it's plus or why it's minus. It's just, since that one is plus, it's going to be different in sign to the other two. Okay, and then the last thing we do is we have what's called a forward path here, and then we have a loop gain here. And so our forward path is G3, G2, G1, and our loop gain is what you see there. And I'm going to go over this more later on. Okay, so here's a much more complicated one. Okay. And again, here I've got a 1 over GS and then just a 1 going in there. So those are two things in parallel. This line without a gain in it has a gain of 1. So I've got 1 over GS plus 1. And it's helpful to keep, put names on each one of these nodes like you do in circuit analysis. So this one we're calling V4. So we know from here going into this function block, I've got two paths, that path and the path going up. And so I can replace those two guys with this one block. Now that I've got those two things going into the summing junction, I don't have to have the summing junction anymore. Okay, so this transfer function here is that summing junction. Back over here, I can take the G1 and move it to the other side of the summing junction. Okay, so G1 moving here, but then I've got to do 1 over G1 on the feedback path. Okay, so I've got G1, G2 on the forward path, and then H2 over G1 on the feedback path. And then this H1 hasn't changed. Now, because we took out, move this guy over and this guy down and applied, when we did that, we lose V3 and V2. Just like when you take a circuit and you're reducing the resistors, the node voltage between those two resistors, when you combine them, is lost. Okay, so if you had like 4 resistors in series, you can have a different voltage between each one of the resistors. Oh, there's Rayon. We'll wait for him to come aboard. I can see those 3 little dots, but I don't know if, oh, there you go. Okay, Rayon, we're about halfway through block diagrams. I've recorded it so you can kind of go back and you can look at it. the most important thing for tonight's lecture, though, is Mason's gain formula, and that's coming up next, okay?
Okay.
Okay. Okay, so basically, like I've been telling Christian, it looks ugly, but this is the same thing as taking a network of resistors and combining them together to come up with the total resistance. Okay.
Okay.
So, and when you do that, let's say you had a resistive network and it had like 4 different voltages in it. Well, when the voltage is between 2 resistors and you've combined those 2 resistors, you'll lose that voltage. And so here you see that we've lost V2 and V3.
Okay.
Can't get those from this drawing because they're internal now. Okay.
Okay. So, when you combine, are you talking about parallel or series, or it doesn't matter?
Right. So when things are in series like this, we multiply. When things are in parallel like this, we add.
Okay.
And then there's one other kind of thing that we call a feedback path. And the feedback path I'm going to be explaining as part of Mason's gain. So don't worry about that. So when 2 things like this, we multiply the 2 things together. So these 2 blocks right here become this block right here, the 1 over G1 plus 1, and the G3 1 plus G3 H3 become just
Okay.
one block. Okay. Here we're combining these 2 things are in parallel. They both have a minus sign. These 2 summers here are basically the same. There's nothing in between the 2 summers. So I can say that this guy is going to here instead and just get rid of this summer. So when 2 things are in parallel, you just add them up. So we've got H2 over G1 plus H1. Just add the 2 up. Now, that's a plus sign there. We're adding them up, but we keep the negative here. So we've got a negative, negative, and it stays negative right there. Okay?
Yep.
Okay. Now, the next step, we've got a forward gain and a loop. And again, I'm going to go through this later, but you can write that out in this form right here. And then the final step is just multiplying these 2 things together. Okay. So this is block diagram algebra.
Okay.
Okay. We can also use MATLAB to do block diagram algebra if we wanted to. So we've got a summing junction here, got a summing junction here. So we can go through and let MATLAB do this for us. So MATLAB can take 2 transfer functions that are cascaded or in series and come up with the result. They can take 2 that are in parallel and come up with a result. And they can do feedback paths and come up with a result. Okay. So here I'm just defining all these transfer functions. And then I'm coming up with the what the final overall transfer function is. So what I did there is G12 was just G1 in parallel with G2. So we just had to add. We can't just multiply 2 transfer functions together. So we use the command series, and that is taking those 2 transfer functions in series. Then we've got a feedback path with H1. And if we look there, H1 has a minus sign there, and MATLAB is assuming that you have a minus sign on your feedback path. So that's all we have to do. So we had the forward path and the feedback path, came up with that. And then we just put the two things in series. And then we have one last feedback path here. It's the feedback path that starts here and goes all the way back. This path has a gain of 1. There's no transfer function in it, so it's just a gain of 1. Okay, so that's one topic, block diagram reduction, and you can do it using MATLAB if you wanted to. But on the exam, and the important thing that I want you to learn for tonight is signal flow graphs and Mason's gain formula. Okay, so here was our block diagram. Oh, sorry about that. But I hit too fast. Here's our block diagram. We've got a transfer function here, and that could be 1 over s. It could be 10 over s plus 4. It could be whatever the transfer function is. Whatever feeds in times the transfer function is what our output is. Okay. Now, we want to simplify this so it's easier to come up with the Mason's gain formula. So what we're going to do is just take this block out of here. So we replace that block with just an arrow and g of s, the function, and that's taken in place of the block. And then E and C are just nodes, okay? Because we're going to have to keep track of the nodes and whether or not they're touching or non-touching and stuff like that. So any questions on just going from block diagram to signal flow graph?
No, seems simple enough.
Okay, good. We went through this earlier. So when you have things in parallel, they go into a summing junction. We've got plus signs and minus signs. So G1 times E1 is a plus sign, so it's plus. G2 times E2 is a plus sign, so it's plus. And then G3, E3 has got a minus sign here, so it's minus, okay? So that's, again, the block diagram representation. If we want to represent it in signal flow graph, same thing. We got E1 times G1 going into CS, E2 times G2 going into CS. And then instead of putting a summing junction here with a minus sign, we just have a minus on the gain. Okay?
Okay.
Okay. Okay, so here's my joke for the night. Mason's gain formula has nothing to do with a bricklayer, has nothing to do with the Knights Templar. It allows the signal flow graphs or block diagrams to be easily reduced. We don't have to do any of that algebra one step at a time. The only problem is that it's a very powerful tool, but it can be used incorrectly. Okay, we've got to define things here. A source is a node, and the signals only can flow away from that node. A sink is a node, and only the signals can flow into the node. So source, only stuff away. Sink, only stuff into. We can make any node a sink node by adding a gain of 1, a path with a gain of 1. We cannot do that with a source node. The source nodes have to exist before the problem starts. The sink node, you can get any variable in the system just by putting a gain of 1 out to a dot outside of the network, and that will give you a sink node. So, can we add a sink? Yes, right here we had C of S. Now, this C of S does not qualify as a sink. We've got one thing going in, but we've got another thing going out. So we just add a gain of 1 going to another dot. If this is CS, 1 times CS is still CS. And now we've got our sync node. This is a source node. There's only things going out of that. Okay. This is a sync node. There's only things going in. Okay.
So with that CS coming back to ES, what is that considered?
That's a feedback path. And it's this, if this gain was 1, then that would be CS here. But since the gain is HS with a minus sign, you
Okay.
take CS times HS and you get ES. Okay?
Okay.
Now, can we add a source node? So that will change our system. We can't do it. So ES is, if we add a gain in 1 here, we'll have an ES here. But that is going to change the system, and we can't do that. Okay? Okay. A path is defined as a connection where we're starting at one point and going to a second point. The branches are continuous. A loop is a closed path, and no node is traveled through more than once. Forward path goes from a source node to a sync node. And again, no node is gone through more than once. Path gain is just the product of the gains of that forward path. Loop gain is the product of all the transfer functions in a loop. And we'll go over non-touching, but basically if you have a loop and it's either enclosed inside of another loop or the corners are touching, those are all examples of a touching loop. If they're non-touching, it means that there's no nodes in common. Once we defined all those things, we've got a formula here, 1 over delta, the sum of k equals 1 to the number of paths, the forward path gain times the delta for that forward path. Delta is defined as 1 minus the individual loops plus the sum of the non-touching loops taken 2 at a time minus the sum of the non-touching loops taken 3 at a time plus the product of the non-touching loops taken 4 at a time. Usually we don't go beyond the first 2 terms. So the individual loops and non-touching loops. If we have 3 non-touching loops, that would be very unusual. Okay, so let's go through some examples.
Sir, I'm gonna ask you if you can post this early so I can get back at it because I'm still at doctor. I'm just waiting, so that's why I logged into class here.
Okay, okay. So I will post. The PowerPoint's already posted, but I'll post the video. Okay.
Okay.
Okay. Sounds good. Oh. Just need to turn on the old projector. See if that works. Let me turn it on and turn it back on again. There we go. Okay. Turn the light on. So the first example is really basic. It was only one loop. So that. So we'll have, let's make this a gain of 1. This we'll call G1. G2. G3. Gain of 1. And then this will be our control. And this will be our, oh, gotta zoom out a little bit here. Guess we can do it the old-fashioned way. Okay. And then we'll have one loop. So we'll make a loop like this. The first thing we do is forward paths. That's when we start at the input and go to the output. Start at the source, go to the sink. So we only have one of those. So that forward path would be G1, G2, G3. Loop. Well, there's only one loop. So that would be loop 1 equals G1, G2, H1. But there's a minus sign here. So that would be minus there. And then we're left with the delta. The delta is always 1 plus the individual loop gains. Excuse me, 1 minus the individual loop gains, but there's a minus sign here. So that's why it makes it a plus. G1, G2, H1. There's also a delta for the paths. So we take out this path here, the path G1, G2, G3. When we do that, what's left? Just this H1 going back, right? But it's not a complete loop because G1 and G2 are gone. So we have no loops. Okay. So that forward path gain is just going to be 1. Okay.
Okay.
Okay. And then now we just put everything into the equation. TS equals the sum of the forward paths, We've only got one forward path, so the sum is pretty easy. Our delta is 1, so it doesn't change anything. And then it's divided by our delta, 1 plus G1, G2, H1. Okay. That's how we would come up with the overall transfer function for this system. Like I said, it's like you had a resistor network, you're coming up with the total resistance. This is the total transfer function. Okay, let's do another example. 2 loops and neither loop touching each other. So I'll make this 1. Again, this is going to be our source. This is G1, G2, G3. Make this 1 again. And this is C. That's 2 loops. So I have 1 loop here minus H1. And we'll have another loop here minus H2. So far, so good?
Yep, looks good.
Okay. Now, if we wanted to, I could add a third path to this, but let's not worry about that yet. So forward path, again, we only have 1 forward path that's starting at the source, going to the sink, okay, without going through any node more than once. So that would be G1, G2, G3. Our loops, you got L1 is equal to minus G1, H1, and loop 2 would be minus G3, H2. And then our delta function, 1. Now it's minus the individual terms taken one at a time. So that's minus G1, H1, minus G3, H2. Okay. Then it's plus the product of the non-touching loops. Do we agree that loop 1 and loop 2 are not touching?
Yep, not touching.
Okay. So we're going to do the product of those. Minus G1, H1, minus G3, H2. We don't have 3 loops that are non-touching, so we're done with our delta. And the transfer function, again, there's only 1 forward path. So that's going to be G1, G2, G3. And now the delta is going to be 1. Minus and minus makes that a what?
Addition?
Yeah, it's going to be a plus, right? G1,
Yep.
H1 plus G3, H2 plus, now these are, it's a product. Negative times a negative gives it a positive. G1, H1, G3, H2. Okay. So that's all there is to Mason's gain formula. We can make more complicated interconnections of transfer functions, and we can always use this guy for the next one. 3 loops, 2 touching. So I'll just start down here. RS. Okay. Make this 1, G1, G2, G3. Now, I need to have 3 loops, 2 touching. So let's make a G4. I could have H1 here. I could have H2 here. And then I can have H3 there. I have to have a gain of 1 here to make this a sync node. There we go. So I've got 2 touching and another one that's not touching. So I've got 3 loops total, 2 of them are touching. If this loop went from this point here, so this is going to be C. I'll call this X1, X2, X3, and this is R. If I had a loop that was going back to R from X2, that would still be touching the loop from X3 to R. Okay. Whenever they share nodes or pathways, they're touching. So again, for this system, I only have 1 forward path. I'll do another one that has 2 forward paths, but for this one, I'll just do the 1 forward path. I've got M1 is equal to G1, G2, G3, G4. I've got a loop 1 is going to be minus G1, H1. Loop 2 is going to be minus G2, H2. And then I've got a loop 3, which is minus G4, H3. My delta, again, we take 1, and now we're going to take the individual loop gains, minus and minus makes these a plus. So it's plus G1 H1 plus G2 H2 plus G4 H3. Oh, it's supposed to be a plus. And then the product of the non-touching loops, taking two at a time. So how many sets of non-touching loops do we have?
Would it be 2?
Yep. So we've got loop 1 and loop 3. And we've got loop 2 and loop 3. I call this loop 1. This is loop 2. This is loop 3. Okay. So 1 and 3 are non-touching. 2 and 3 are non-touching. That's what I have there. So my overall transfer function TS is going to be G1, G2, G3, G4, 1 plus G1, H1 plus G2, H2 plus G4, H3 plus loop 1 times loop 2. Well, they're both negative. So negative times a negative is a positive. So that would be G1 H1 times G4 H3 plus L2 G2 H2 times G4 H3. Any questions on how I got that? Okay, let's do one last one. Instead of using G's and H's, I'm going to put in actual transfer functions. And I'll make another path going forward like this. So again, R, it's again 1. I'll make this one 1 over S. I'll make this 4 over S plus 10. I'll make this 7. I'll make this gain 3. I'm going to have a gain of 1 right here to make it a sink. This is CS. So there's a gain of 1. Up here, I'll make this a gain of 2 over S squared. I'll have this have a gain of -2, and I'll have this be a gain of -4. Let's make that a +4. Okay. So does that look messy enough?
Yeah.
Okay, cool. So, okay, so we've got two forward paths. M1 is going to be 1 and 1 over S times 4 over S plus 10 times 7 times 3, right? And then the second path, M2, is going to be 2 over S squared. Everyone's, I got that. So I've got two paths that take me from R to C. I've got the path right down the middle, and then I've got a path that goes over the top. And so let's see, 21. So that would be 84, right? 84 over S plus 10. And then that's 2S, 2 over S squared. So not a problem there. Okay. Then we have to come up with our loop gains. We've got loop 1 would be minus 2 over S. Does everyone see where I got that?
Question, sir. I got a question.
Sure.
That's 3. That's 3 ties in what way?
This 3 right here.
Yeah.
Okay, when I go down this path here,
Okay.
I've got a gain of 1 over S, a gain of 4 over S plus 10, a gain of 7, a gain of 3, and a gain of 1.
Okay.
So
All right.
that's where those come from. And
So
then when I
that
go,
that top one is the 2 over S squared.
right.
Okay. All right. Got it.
Okay. And then this loop gain is 1 over S times a minus 2. So it's minus 2 over S. And then I've got a loop 2, and that's going to be 7 times 4. So that's a plus 28. Okay. Then I've got to come up with my delta. Always start with a 1. And now we take our individual loop gains and we're subtracting them. So that's plus 2 over S minus 28. Right? Because that's a plus 28, so that has to be a minus 28. And then are these two loops touching L1 and L2?
No. Is it?
No. Okay, so then it's going to be plus loop 1 times loop 2, right? And that loop 1 times loop 2, it's a minus 2 over S times 28. So that guy right there becomes minus 56 over S. That making sense?
Yeah.
28 times 2 is 56. S, and since it's plus, that's a minus there. There's no minus here, so it doesn't cancel out.
Okay.
Okay. We're still left with the delta functions. If I take out this first path here, there's neither one of these loops exists anymore. So delta 1 is just 1. Delta 2, if I take out this path, do any of the loops survive?
Yeah.
This guy in the middle, right? This guy here, since they took out this node, this path doesn't exist anymore. right? But these two nodes aren't affected if I take out the second forward path. So I've got 1, and now this loop gain is positive 28. So 1 minus 28. Okay.
Yeah.
Okay. So now my overall transfer function, TS, I've got for my first path, it was 84 over S times S plus 10. My delta function is 1, so it just multiplied by 1. So that's going to be 84 over S plus 10. And then I'm adding this next one, right? But what 1 minus 28 is a minus 27.
Yeah.
So I'm going to get, well, what's 2 times 27?
54.
54. So minus 54 over S squared. Okay. So those are my two forward paths. And then my delta on the bottom is just 1 plus 2 over S minus 28 plus, oh, excuse me, minus 56 over S. Does that look good?
Yeah.
Yeah, okay. Now, if we wanted to, and we wanted to make these ratio polynomials, okay, I would multiply through by S squared plus, excuse me, S squared S plus 10. So top and bottom. Right? So I've got 84. So T of S equals 84S, because this is S plus 10. So one of the S's don't cancel. 84S minus 54 S plus 10 over so that's going to be S squared S plus 10 plus, well, one of the S's cancel out, so that's 2S S plus 10. Nothing cancels out on the next one. Minus 28 S plus 10. And then we're left with minus 56 S plus 10. Okay. Because the S here is going to cancel out with one of the S's.
So,
Oh, hang on here. S squared right here. That should be S squared.
okay.
So again, we can simplify it some more. We got 84 S minus 54 S, that's going to be 30 S, right? 30 S minus 540 over, well, that's a, oh, this is going to take more work than I thought. S cubed plus 10 S squared plus 2S squared
Plus
plus
20.
20 S minus
Minus
28 S cubed, right? Because that's S cubed plus 10S squared minus 280 S squared minus 56 S minus 560. Did I do that right?
Yeah.
Yeah, it's still ugly looking though.
It is.
Okay, so I guess I should read it all the way. TS equals, well, the 30S in top minus 540, and then if I combine the S cubed terms, I've got minus 27 S cubed, and I've got S squared terms. I've got plus 12 minus 280. I got to grab the calculator for that. Clear. 12 minus 280. Oh, clear. 12 minus 280 minus 268 minus 268 S squared. That's all the S squared terms. And then I've got 20 minus 56 minus 36. And that's an S minus 560. I'm still not done. I got to divide top and bottom by minus 27. So I got 30 divided by 27, minus sign in front, S minus 540 divided by 540 divided by 27, 20. Oh, that would make it plus 20 divided by S cubed minus 68 divided by 27. Doesn't make you a nice round number, so that would be plus 268 divided by 27 S squared. I don't think 36 divides evenly either. No, it doesn't. 36 over 27 S, then 560 divided by 27. Nope. Oh, that's a plus sign. Plus 560 divided by 27. Okay. So we can go from here to here with Mason's gain formula. If we didn't have Mason's gain formula, we would have had to combine this guy, multiply this guy by that guy, combine this guy, multiply the three together, Take that guy, multiply it, combine it with those guys. So you could do it either way, but I think Mason's gain formula is simpler. Okay?
Okay.
Okay. So I was mentioning to Christian that we're going to have a review for our midterm. So I'll post a sample exam tomorrow, and then Wednesday night we'll do the review for the midterm.
Okay.
Okay. And then if you guys aren't ready, I can postpone the midterm until you're ready sometime next week. Okay. And I'll send you the midterm exam when you're ready for it. And then when you're done, scan it in and send it back to me.
Okay.
Okay. Any questions, gentlemen?
Are you gonna put this on tonight?
Yeah, I'll put them on. I'll put it on tonight.
Okay.
Okay. Sounds good.
All right.
Any other questions? Okay. Well, you guys have a good night. And hopefully, Christian, you're feeling better. And hopefully, Rayon, your life isn't so hectic. Okay.
All right. Have a good one.
Yeah, you too.
All right.
Yeah,
Bye.
thank you.